Good morning, ladies and gentlemen. Today I'm going to be presenting some solutions for the SMO 2018 paper. So today I'm going to be covering questions 21 to 25. So let me just activate a pen. All right, so question 21 is on algebraic manipulation. So this is the question. If x is a real number such that x cubed plus 1 over x cubed is equal to 18, we want to determine the value of x plus 1 over x squared. So first, I want to start off by noticing and expressing to you that these two things appear to have a similar form, right? You have x cubed plus 1 over x cubed here, and you have x plus 1 over x here. So now you must find a way to relate these two things, right? And you realize that you can actually do that through some expansion. So if I expand x plus 1 over x cubed to the binomial series, I actually obtain this result over here. And if I simplify it a bit, I get x cubed plus 1 over x cubed, which is actually this term over here. And then x plus 1 over x, I obtain twice, right? So I found a nice relationship between these two things. So this is the equation we found at last slide. So now what I can do is I can substitute u as x plus 1 over x because this appears twice and we want to find a nice way to evaluate it. So after substituting, I get u cubed, which is this term over here. Then I get minus 3u. This is 3u. I bring it over, it becomes minus 3u. Then this is minus 18. This value is given as 18 in the question itself. So all of this evaluates to 0. So I now realize that I can actually factorize this to get u minus 3 times u squared plus 3u plus 6 equals to 0. So now I think to myself, what does this return? And it turns out that this is always positive. This function always returns a positive value. And if I graph it out, I obtain this result. Notice how this is the x-axis and all the values are always above the x-axis, so it's always positive. Another way to think of this is that a quadratic equation ax squared plus bx plus c equals to 0 has no real roots if b squared minus 4ac is less than 0. We call this term the discriminant of the quadratic equation. So for x squared plus 3x plus 6, b squared is going to be 9, then minus 4ac is going to be negative 24. You sum those two, you're going to get negative 15. That's actually less than 0. So it has no real roots. It does not intercept with the x-axis. Hence, it is always greater than 0. So for this equation to be equal to 0, we realize that u must be equal to 3. So that is the only solution to our equation over here. Hence, x plus 1 over x is equal to 3 because we substituted that in. And then we want x plus 1 over x squared. We simply square that thing and we get 9. So that's question 21. And I highlighted the main theme over here. So in my opinion, the overarching theme is a bit of algebraic manipulation, just realizing how the things fall into place. This is question 22. So when expressed as a fraction in the lowest terms, you have 1 over 1 times 2 times 3, and so on and so forth. And you notice a nice pattern. The first three terms are 1 times 2 times 3, then you go 2 times 3 times 4. So you notice that this is actually in the form of 1, n minus 1, that's going to be 1, for example. N, that's going to be 2, for example, then n plus 1. This is in the form every term, right? And then we realized through partial fractions that I can actually express it as such. So you can actually expand this side out and see if it evaluates to the left-hand side, which it does. So the nice thing about this expression over here is that I can now rewrite my initial expression in the question, and I realize that all of these things inside cancel because there's 1 minus 1 positive, and this just occurs throughout the inside. So I realize that the only things I'm left with is the very first term and the very last term, right? So that's a very cool way of simplifying our problem. So after cancellation, we actually obtain this thing over here. And this thing is fairly straightforward to evaluate through some arithmetic. And it evaluates as such, and we can simply add the two terms up. This is in its simplest form. Right. My bad. The overarching theme, in my opinion, is this thing called telescoping sums for question 22. So telescoping sums is when I find a nice way to express a term in terms of two expressions, which nicely cancel out when I work it out. Yeah. So now we have question 23. So I have alpha, beta, and gamma, and they satisfy this equation over here. So you realize that we are working with a cubic over here. We are working with a cubic. X cubed is the largest power of x within my expression. So over on this side, we realize that we're given a product of the cubic expression's roots, right? So there's actually a nice way to link these two things together, given by Vieta's formula. So what Vieta's formula says is that for a cubic equation, ax cubed plus bx squared plus cx plus d, so I can express it as the product of this, right? Where alpha, beta, and gamma are the roots of the equation. So these statements must hold true. So this is given by Vieta's formula. So you have alpha plus beta plus gamma. We call this the sum of the roots. It's going to be negative b over a. Then you have the sum of these terms equals to c over a. And then the product of the roots is equal to negative d over a. This is a very handy result over here because we have the roots on this side. We have the roots on this side. And over here, we already have all the coefficients. We have a is equal to 1, b is equal to negative 18. Then we have c is equal to minus 122. And then we have d is equal to 161. So now all we have to do is we substitute our values in. We have sum of roots 18, sum of these terms negative 122, and product of these terms negative 161. So at the end of the day, we want to obtain alpha squared plus beta squared plus gamma squared. And there's a nice way to evaluate this. All I have to do is take this term and I square it out. When I square it out, I realize that I get this bit, which has a known value. I simply take 18 squared. And I have this bit, which also has a known value, which is negative 122. So I substitute those in and I get my final result of 568. So the overarching theme is Vieta's formula. It's a very nice way to relate the coefficients of polynomials with the sum of the roots and so on. So next you have question 25. So this is an example of the binomial theorem, which we will see later. Oh dear, I think I've skipped forward a bit. Oh my bad. Okay, here. So next we move on to question 24, which is about just manipulating a bit of inequalities. So how many integers x satisfy this inequality over here? So we start off by realizing that we can reorder the terms. We bring the 2018x over to this side, and then we can complete the square. Completing the square is a nice thing that leaves us with a single x, and then we square some term inside. You can expand this out to check that this equals to this. And then we can bring the quarter over to that side, and then we express it as such. So after that, what we do is we take the square root of the term on the left, because it's a square, right? And when you have inequalities, how it works is, let's say this is my number line, okay? I have this to be my number line. So that's this value, 8077 over 4. For simplicity's sake, I'm simply going to call it x naught. I'm going to call it x naught, all right? So what this inequality says is that it's equal to all the values equal to and less than, right? That is a visual representation of this. So when I take the square root, what I really want to get is I want to get something that is within the square, within the minus square root of x naught and the positive square root of x naught. So I want something that is in between this. So that's what it's saying. So now I can bring the half over, and now I get this very nice thing. But notice that this one looks a bit ugly, so I can set some boundary conditions. So notice that 2025 is equal to 8,100 over 4. That's 2025, and 8,100 over 4 is actually greater than this thing, and 2025 is a perfect square. It's 45. You can repeat the same process, 44. So you notice that this term over here is between 44 and 45. So next what I can do is I can substitute that in, and I identify that x must be within these bounds. And if I try to work it out, I realize that there are 90 integers which satisfy this inequality. Last but not least, we have question 25 with the binomial theorem. So we have an expression over here, and we want to determine the coefficient of x in the following expansion. So you realize a lot. You realize that an awful lot of these terms look quite similar, right? You have 1 minus x, and then you take some power n, and then you realize that the minus and the positive signs alternate, right? The minus and the positive signs alternate. And a nice way to represent this is by taking -1, and then you take the nth power. So you realize that it looks an awful lot like this. So you realize that the coefficient of 1 minus x to the power of k is equal to minus k. Hence, the coefficient of x in the expansion is given by this summation over here. And you realize that it can be very nicely evaluated through this. You simply sum 1 minus 2, 3 minus 4, and so on and so forth. All of these individual sums evaluate to -1, and then you multiply it 1008 times to obtain -1008. You sum it to 2017, and you get 1009. So that is the final question. Thank you so much, and I hope you have a great day.